I think we'll get started there a minute after 3 o'clock. So hi everyone, thanks for joining this week. This is our first sea ice talk of 2023 in the IGS Global Seminar Series. So thanks everyone for being here. We're going to continue kind of one sea ice talk per month through the winter and spring, kind of leading up to the next IGS Sea Ice Symposium in Bremerhaven this June. Magnus's image here on the Zoom call is the logo for the IGS Symposium, and he was just telling us that the abstract submission should open up potentially next week or the following week. So look for some more information on that, probably coming through CryoList or through other networks available. So this week we've got two great talks from Patricia and Robbie. Robbie is a postdoc at the University of Manitoba. He recently defended his PhD at UCL in London. And Patricia is a postdoc at NCAR in Colorado. Robbie's going to be talking to us about Antarctic sea ice, and Patricia's going to be talking about the role of emissions in sea ice decline. And we're going to get started with Robbie. As per usual, we'll just hold off on questions until the end of Robbie's talk, and then we'll open it up and we'll use the raise hand function or throw your question into the chat, and we'll get to it at the end of the talk. So Robbie, I'll let you take it away.
Thanks, Dave. I'll just share my screen. So, yeah, that was a good background actually, because I just finished a PhD on Arctic sea ice, and now as a postdoc, I'm moving to Antarctic sea ice, which is interesting because I think a lot of the sea ice remote sensing community is starting to move more to Antarctic sea ice through advances in technology and also changing like high-level priorities, particularly as Antarctic sea ice is starting to show clearer signs of decline now. It's becoming more relevant in a climate change context rather than just a climate system context. And a lot of the work I'm involved in now is in situ. So we do remote sensing, but it's also really good to actually go and directly sense what's going on, because when you just retrieve things from space, you can often get a bit muddled by compensating biases, so getting the right answers for the wrong reasons, and you can only really tell when you go and validate. And validate's a tricky and slippery word, but I'll come on to that later. So specifically, there are some difficult challenges. Oh yeah, I'll just introduce the people that I work with, because I put my name and my name only on the title slide, because a lot of this talk is my perspective and my opinions, and these are the people that put up with me, but we don't necessarily share all of our views. So we do a lot of great collaboration, but there's a really healthy spectrum of opinions in the sea ice thickness community in particular. So this is the team that's most involved in a lot of the sea ice thickness retrieval work that we're trying to do in Antarctica. So I don't want to give a talk about how important sea ice thickness is, so I'll just quickly recap it. That the three ways I think it's most important is as an indicator of climate change. So it thins in response to a warming climate is the simplest way of describing it, but it also indicates lots of changes in the individual systems like the atmosphere, the ocean, changes in dynamics, etc. It's a really useful evaluator as well of models. So if we want to check our models are doing well, we can check against sea ice extent, but if we want to check really the physics of complex models, sea ice thickness is a really useful evaluator. And sea ice thickness is also interesting because it's a prognosticator. So we can look at where the sea ice is thick at the end of winter, and that provides an indication of what sea ice is going to survive through to the summer minimum, and it gives us a forecasting capability. And again, I don't want to give a talk about how we retrieve sea ice from space, but I'm just going to give a bit of background on roughly how we do it, and then move on to some of the trickier issues. So in both hemispheres, the radar method of retrieving sea ice thickness from space is kind of gloriously simple in its essence, that we bounce radar waves off the sea ice and we measure how far away they are from our satellite. And then we bounce radar waves off the water that's nearby, and we find the water is a little bit further away. And that difference in range, the amount that the water is further away from the satellite than the sea ice, tells us about the sea ice freeboard. It tells us how far the sea ice is sticking out of the water And from that, we can think a little bit about how much the snow on top is weighing it down, and how dense the sea ice is. And we can convert the amount that the sea ice sticks out of the water, the freeboard, into the sea ice thickness. So there's quite a lot of uncertainties and there's quite a lot of steps in that, but I actually think it's a really nice method to work on. Kind of, especially because of its sort of classical origins, that you could have explained this to Archimedes and he would have nodded his head. So this is a figure that Alec Petty recently put out in a paper, and I think it's a nice contrast to the simplified schematic I put on the last slide. So when I said we bounce radar waves off the sea ice, lots of methods using something called KU frequency radar does rely on us truly bouncing radar waves off the sea ice and not just off the snow surface on top of the sea ice. So it relies on us penetrating the snow to reach the sea ice, but it also relies on loads of other stuff. It relies on us accurately being able to find the water nearby to the sea ice flow. It relies on us understanding how sea ice roughness plays into the reflection of the radar that we see, and a whole bunch of things to do with the ice thickness distribution. So on what length scale can we use this approach? There's lots of challenges to the approach, which makes it quite hard. And I guess the position that I am coming to occupy in the sea ice thickness retrieval community is one of towards the skeptical end. So I think it's harder than I think the average person does. You could call me a pessimist maybe. And there's 4 really key things that I think about that this method relies upon. So the first one is the waveform. So you need to understand when your radar pulse returns to your satellite, having bounced off the sea ice, you need to interpret that radar waveform. And I'll show you one in a sec. But the radar waveform is not just a spike. It's a complicated sort of shark's fin shape, and we need to pick just one point on that shark fin to say, okay, here's the sea ice surface. Sea ice density. So when we convert our amount that the sea ice is sticking above the water into the total thickness of the sea ice, we need to know its density. We need to know the amount that the snow is weighing it down. So if you have a lot of snow, the ratio of the freeboard to thickness is much lower. So we need to know snow depth a priori, so before we even look at our radar data. And we need to be sure that the radar is penetrating the snow in the case of the most common satellites like Cryosat, MVSat, Sentinel-3. So we need to be sure of the penetration properties of the radar waves. And I'm going to talk about, here's a picture of the radar waveform first, just to illustrate that it's not that simple how we pick a single height from the wave that returns to our satellite from the data that we see on the screen. And there's quite a dark art to interpreting these waveforms that I'm not a specialist in. So I'm going to leave that alone, and I'm going to focus on these 3 variables, because these 3 variables are the most interesting, I think, in terms of Antarctic sea ice, in terms of porting over what we know about the Arctic into the southern hemisphere. And there's some unique geophysical aspects of Antarctica that I think make it difficult, and I think also clash in an awkward way with the very electromagnetics focused approach that a lot of radar altimetry folks use. So to really get to grips with sea ice thickness in Antarctica, we need to understand EM radiation, we need to understand scattering mechanisms and all of that stuff, but we also need to understand the climate and the geophysics of the sea ice that we're looking at. So it's quite a tricky problem. Just taking sea ice density first. So the southern hemisphere sea ice has a bunch of really interesting features. We tend to just assume a density for the sea ice, which is mostly first-year ice in Antarctica. But we're really short on high-quality in-situ data. And the in-situ data we have, we often aren't exactly sure of the methods that were even used, because a lot of it's quite old, from the 60s and 70s, but also how those methods relate to each other, because there's a couple of different ways of measuring sea ice density. And there's also geophysical issues that mean that the density may not actually be spatially consistent, temporally consistent, or similar to the Arctic. So we have superimposed ice in the Antarctic, particularly in the areas that are around in the summer, in the Weddell Sea and the Ross Sea. And that's when you get snow melting and then refreezing as a cap of fresh ice on top of the sea ice. And it's not even clear whether we should treat that as sea ice in our retrievals or not. But if you do treat superimposed fresh ice as sea ice, then that's going to affect its density. And I'll show you a picture in a second of a thick layer of superimposed ice that we encountered recently. We also have snow ice, and I'm going to mention that in a second as well. So snow ice is where you accumulate so much snow on top of the sea ice that you weigh down the sea ice flow to the waterline, and then in fact underneath, and the seawater floods the snow and turns into ice. And that's a very distinct form of ice. It has a very distinct density compared to traditional frozen seawater, because it has this matrix of snow crystals inside it. And finally, and I'm really glad this is coming to the fore in Antarctic sea ice research recently, is platelet ice. So the accumulation on the base of the sea ice of this really interesting accreted ice that comes from outflow of fresh water underneath ice shelves and marine terminating glaciers. And that certainly can really change the density quite significantly, because it can be quite fragile and it can run quite deep, but it has a large porous void space, basically. And here's a core we took of some snow. So you can see towards the top of this core that we took in March in the Weddell Sea, there's some really hard crystally snow that's turns out doesn't emit radiation very well. We can't penetrate it with radar very well. And then it just turns towards the bottom, towards completely bullet hard freshwater ice that was superimposed on the ice flow. And we checked that to make sure that it was indeed fresh ice. We checked the salinity, and if you get 20, 30 centimeters of that on your ice flow, it's going to be very difficult to identify anything like a snow sea ice interface, and also factor that into your density. This is a plot I made for this talk, actually, about just how much snow falls on Antarctic sea ice. So thinking about these zero freeboard situations, or even negative freeboard situations, if you just add up all the snow that falls onto the surface of sea ice in an atmospheric reanalysis data set, it's about 3 times as much, which is a lot. And that doesn't all necessarily stay on the sea ice. So some will sublimate away, some will blow off into leads. But just as a ballpark figure, sort of rule of thumb, it really is quite striking that Antarctic sea ice during its cold season, during its accumulating season, just has a lot more snow fall on it, and that has quite profound effects for the nature of the snowpack and the weight of the snowpack. And I'll come back to this plot in a minute. But I just want to draw this idea of a zero freeboard line, of the ratio, the amount of snow that you can get to ice thickness that drives your sea ice flow under the water. And it's not actually very much. I'm constantly surprised when I draw this plot that how little snow it actually takes to accumulate on your sea ice flow to push it under the water. And it's also a nice simple relationship. It's just y equals x over 3 for some typical ice density and snow density values. I picked 900 kilos per meter cubed for the ice and 300 kilos per meter cubed for the snow. So you can, hopefully you can see my mouse, that you can see for sea ice of about 1 meter, you can't have a lot more than maybe 35 centimeters of snow before you start to push that under the water. And that presents real problems for radar altimetry. As soon as we hit 0 or that negative freeboard zone where the ratio of snow to ice thickness is too high, we're really in trouble with regard to radar altimetry. And that's a problem for Antarctica in particular. If we think about this in a slightly less intuitive way, in terms of the snow water equivalent of the snow that's fallen in millimeters. So if we just melted that snow and saw how deep the residual water was, you can see that at the top of this here, 300 millimeters, going back to that plot we had before, you could pretty easily get 300 millimeters of snow water equivalent fall on an Antarctic sea ice flow over the course of a winter. And to support that with a positive ice freeboard, so to actually have some ice sticking out of the water that you're going to measure, you need an ice thickness of about 3 meters. You need your ice to really be quite thick. And for a predominantly seasonal ice pack, that's a struggle. So it's no wonder that we see these 0 and negative freeboards. So so commonly in the Antarctic. So I've banged on about these zero freeboards, and it poses an obvious question that if the freeboard of the sea ice is so often zero and it's so often negative, why is it that when we bounce these radar waves around on Antarctic sea ice, we see so often them bouncing off surfaces that appear to be above the local waterline? So when we bounce our waves off the waterline and we bounce them off the sea ice flows, there often is a difference, which might make you think, oh, the freeboards actually aren't zero so often as you're saying, Robbie. But there are other reasons that the radar would bounce off parts of the snow and even the snow surface to make it look like you have a real ice freeboard when actually you have a zero ice freeboard or even a negative ice freeboard, and you're just looking at the height of the surface of the snow. In other words, we're failing to penetrate the snowpack quite often with radar waves. One reason that we might see this is brine wicking. And I must confess that I was a cynic about this for years of my PhD, but I've recently come to accept that it is real based on some pictures like this that colleagues have shown me of a zero or negative freeboard situation where seawater wicks up the snow, and you can see it in this picture, to a very distinct height. There's a very sharp line where the seawater is wicked up to in that porous snowpack. And when that happens, the radar waves are not going to penetrate that seawater sodden snow. The dielectric permittivity, the radar reflectivity, if you like, of brine is very high. In fact, the radar reflectivity of just water is very high. So we're not going to penetrate that. And this scenario is going to look like we have a real ice freeboard, a real positive ice freeboard, when actually we're just looking at a layer to which the brine is wicked upwards. Here's another really nice picture, I think, of an experiment actually where Rob Massam dug out some snow from Antarctic sea ice and took it back to the lab and sat it in some water and saw how far the brine could actually wick up the snow into the against gravity, basically. So I think we really need to do some work, and it's going to be difficult work to look at how pervasive this phenomenon is in Antarctica. And if you have a zero freeboard, how likely are you to see this? We can also have scenarios where we have radar reflecting in the snow from other reasons apart from just brine. So this campaign we just did in the Weddell Sea in March, we saw some really striking features on the left. I've already shown that photo of superimposed ice, just bullet hard fresh ice, density of 950. Radar waves aren't going to penetrate that like they're going to penetrate snow. But we also see ice layers. So we dug this ice layer out of a snow pit. And that is really going to confuse a Ku band photon, a Ku band radar wave that's trying to make its way, if you will, to the ice surface, and it's going to see this and it's going to reflect. And if we're not very careful, we'll interpret that as a real ice freeboard. So we'll interpret that as sea ice sticking out above the waterline, and we'll try and convert that into thickness erroneously. So we have a radar. The group I'm part of at CEOS has a Ku band radar, and I'm going to ask you to look at the blue line on this, which is the typical frequency that we see from satellites like Cryosat, Sentinel-3, ENVISAT, ERS. And we can see that when we take this in-situ radar out, so it's literally like a radar gun that you catch cars for speeding with, it's the same frequency in fact, and we point it at the snow, we see that a lot of power comes first from the snow surface. So a lot of Ku band radar waves don't even make it into the snow. They bounce straight off the snow surface. And then in this snow pit, you can actually see it on the photo. There was an ice layer, so an area of the snow where you couldn't stick a knife into it. It was so hard. And a lot of Ku band radar power came back from that. And then we got down to a layer of old snow that was around in the summer. So we did our campaign in the winter, but we had some snow and an ice flow that was around in the summer, and we saw that the snow that was around in the summer just didn't really emit any of these radar waves at all. So certainly the radar waves that were emitted from our instrument on this campaign barely made it to the sea ice surface. There's no clear signal from the sea ice surface here, and this is really a puzzle, right? So if satellites were doing this and they were just bouncing most of their radar power off the off the snow surface, for instance, never mind anything below that. In the Arctic, at least, we really see massively overestimated sea ice thicknesses, and we know that's not happening. So we know that although the uncertainty is very high, the bias of sea ice thickness products it's not massive in the Arctic, where we have good evaluation. So we're at the moment trying to reconcile these in-situ radar results of snow radar penetration to satellite-based products, and it's not trivial because there are quite deep issues surrounding the length scale on which we're working, and the length scale over which radar reflections are coherent, and technical stuff like that. But I think this is a really nice plot of how, if you go out onto the sea ice with a radar gun and point it at the snow and point it at the sea ice, it's not trivial. And in fact, we've not yet been able to reproduce the assumptions on which sea ice thickness retrieval algorithms work. And that's not to say this is some bulletproof disproof of what's going on, because there's good evidence that sea ice thickness products certainly don't have a significant bias. So I think the conclusion, if I could ask you to just draw a one-word conclusion from this work, is caution. That particularly in Antarctica, where we see these ice layers, we see sometimes remnant snow from the summer. In other areas, we might see brine wicking. It's all about caution and trying to really grapple with the geophysics of the sea ice as well as the radar physics. There is a bit of interesting hope, and Rosie Willett in my group is working really hard on this aspect at the moment. That and this is a bit radar nerdery, so feel free to switch off for 30 seconds if you need to. If you actually look at the radar waves that return in the opposite polarization to which they're emitted, so we mostly work in co-polarized radar world where we emit in one polarization and receive in the same. But if you do start to receive in the horizontal polarization, having emitted from vertical polarization, you do start to see a lot deeper into the snow. So the cross-pole approach to sea ice thickness retrieval is looking certainly interesting, if not very promising at the moment. But that's a technical detail for the radar folks. Coming back to the broader themes of what I've tried to cram into this like 25-minute little talk. I'll skip this slide. It's too much. I thought I'd spell out at the end my personal dream roadmap of where I'd really like to see the community go. So we certainly need to, number one, develop more snow loading products for Antarctica. So we need to have gridded data sets of not just how much snow has fallen from the sky, which is what I plotted earlier, but how much snow we think is actually sitting around on the sea ice, and weighing it down, metamorphosing, reflecting, permitting radar to go through it. We really need to develop those. We really need to bridge the gap between what we're seeing with in-situ instruments that we drag around on sleds and what we see from airborne radars like Cryovex, Operation Icebridge, and also satellite instruments, because they're just not matching up, and they haven't really matched up over their history. So this isn't some new finding that we have with our instrument. If you go back to Rosie Willett again, her PhD work in 2010, it wasn't matching up then. So we really need to bridge this spatial scales gap. And we really, for Antarctica in particular, we need to start looking at much more radar independent validation, with upward looking sonar buoys, in my view, being the gold standard. So a lot of the validation gets done by Operation Icebridge, which uses a radar to find the sea ice snow interface and measure the snow depth, in fact, quite often as well. And it's no surprise that radar is subject to the same biases that satellite radars are. So if one assumption is faulty, it's often going to be faulty in both the validation and the observation. So we really need to find some radar independent validation to be using more in Antarctica. And it does exist, it is out there, but it's sparse, and we need to bolster it. Most importantly, this is my final soapbox moment where I'll impose my views upon you over the internet. I think we need to move to a situation in our language where we move from ideas around validation to evaluation. So I often read about various data sets, actually, not just sea ice thickness ones, being extensively validated. And that has a very binary connotation to me that implies that if you've essentially extensively validated something, you've gone out time and again and you've shown that the product is correct. But these validation data sets, as I've implied above, are often quite prone to uncertainties. And in the case of our in-situ radar, it's subject to constraints based on the spatial scales. So when I talk about looking at how good sea ice thickness products are, I'm trying to talk about evaluating them and comparing one uncertain data set to another data set that is itself uncertain and is itself subject to context and caveats. So it's kind of less fun to go out and evaluate a product rather than go out and validate it. But I think it's a subtle change perhaps that we can make that would lead to a much more productive discourse in terms of these products. That's me all done. If anyone's got a couple of questions, I don't want to eat into Patricia's talk. We've got perhaps a couple of minutes for questions. I thought I'd put a lighter slide up from our campaign of, you start to go a bit mad when the weather's bad, when you get stuck on these ships, and I start to see faces everywhere on these ships. So I thought I'd leave you with some faces that I found on the German icebreaker Polarstern that maybe you can look at while you think of a question.
Fantastic, Robbie. Thanks so much. With that, while everyone is trying to find all these faces, we'll open it up for some questions.
Yeah, great. I'm trying to work out how to, there we go, unshare my screen.
Inga, you are first up on my screen here.
Thank you. Sorry, I'm having problems with technology this morning. Thanks, Robbie. That was a great talk, really interesting. I always like it when people say platelet ice is important because that was what my PhD was on and a lot of my work now. So thank you for that. It might be more of a comment than a question, but with the ULS sensors, that's the upward looking sonar ones, in platelet ice regions, we've had real problems with them accreting platelet ice so that they don't give any useful data at all. So as part of your roadmap, the platelet ice region, what kind of technologies would you envisage rather than ULS?
Oh, well, just even defining sea ice thickness in terms of platelet ice is a bit of a nightmare because the reasons that sea ice thickness is important are kind of a bit different in a situation of plateless ice where you can almost wash away a whole like layer of plateless ice with a big gust of wind. So I don't really know. It's certainly a conflict in my roadmap between taking care of platelet ice and taking care of upward looking sonar buoys. So I don't have a nice answer for you, I'm afraid.
Yep, cool, thank you. Yep, I think, yeah, the currents can move around some of the platelet ice. Our McMurdo Sound stuff is fairly stable, but yeah, really hard to measure. But yes, thank you for your roadmap. That was really cool.
Great, thanks. Stephen.
Oh, yeah, very nice talk, Robbie. Yeah, I've long thought, like you, that we should say evaluate rather than validate. And you said validate is more fun to say, but you can also enjoy saying invalidate. But my question is, you pointed out what you need in order to do the calculation. You need the penetration depth, the snow depth, and the sea ice density, but you also need the snow density. I don't think you said much about that.
Yeah, in fact, I think actually, if you're assuming total penetration of radar, the total weight of the snow is much more important than either the depth or the density, because it's the speed, the amount with which radar waves are slowed down by the snow is very proportional to its weight, and also that the obvious factor of how much the snow weighs down the flow is the weight. So yeah, you're right. I think it's actually the weight is almost the holy grail, and the ratio of depth to density is perhaps not as important. So I totally agree with that point.
But if you're using the laser, you're getting the snow depth, not the snow water equivalent.
Yeah. So for radar, I lean towards the snow loading, the snow weight, but then for LiDAR approaches, for sure we need the depth. And I have sympathy with the LiDAR folks on that, because I actually think depth is harder to model than SWE, than the snow weight, because in terms of modeling, we have a much better idea of how much snow falls from the sky in terms of its weight than what its density is when it shows up on the ground.
I'm muted, still catching up after the holidays. Anyone else? Alec?
Yeah, you talked a bit about like bipolar, Arctic versus Antarctic. Then you kind of showed some plots around SWE versus freeboard versus thickness, which, potentially offer a way to approach this that doesn't care about the pole you're in, right? You just kind of can look at those kind of external forcings potentially as a way of seeing which areas might be areas that could provide problematic satellite retrievals. Have you thought about that in terms of making it less kind of hemispheric dependent, these challenges?
Yeah, one thing that's really puzzling me at the moment is increased lead fraction in Antarctica, that trying to work out if more snow is blown off the sea ice in Antarctica than in the Arctic, because it's all well and good adding up what falls from the sky, but if the lead fraction is really high in Antarctica, we could lose a significant fraction of that, and it could actually make it more like the Arctic. And there are some sort of quite deep physicsy reasons why sea ice concentration could be lower in Antarctica, and therefore it really complicates the issue, at least in my mind. So I think so. I think some like an ASOSIM style approach where we just summary analysis at a given density is definitely the first step, right? For sure, it's what we need to do, and then work a bit from there.
Interesting. Roger.
Yeah, thanks very much. And well, first of all, congratulations on just passing your thesis defense.
Thank you.
Harking back a little bit to Inga's question, actually, about the ULSs, if it's a fair one for you. What kind of underside do they see in the ice? Because I know a little about, I think it's called frazzle ice under ice shelves, which we've tried to image with seismic surveys from the surface. And I wonder whether ULS observations from underneath might be misled by that.
Yeah, for someone that spends his whole life screaming about how we shouldn't take observations at face value, I actually am a chronic offender at taking upward-looking sonar data at face value. And I think there's a lot to be said about particularly ridged ice with keels, about whether the upward-looking sonar buoys are really understanding that element of sea ice thickness properly, and as you say, whether they're really looking at layers of sort of suspended drifting frazzle ice. And to be honest, I wouldn't like to opine too much on that, because I'm definitely not an expert in terms of upward-looking sonar. I firmly prefer looking down from above.
Smashing. Thanks very much. Congratulations again. Cheers.
Maybe I'll just open it up. Inga, do you have a comment to add on some of this ULS discussion?
Not really. I'm also not a ULS expert, but yeah, we did have issues with one that we had on a cryosphere innovation buoy that basically just turned into a giant blob of platelet ice and stopped transmitting useful data. So yeah, I think in the Arctic it's probably very reliable, but I think in those platelet ice parts of Antarctica there's probably an alternative technology that I'm not aware of yet that we need to think about.
Yeah. Interesting. Well, thanks so much, Robbie. That was a fantastic talk, a little crash course on radar remote sensing of Antarctic sea ice thickness. So thanks so much. We're now going to move over to Patricia, who's going to shift poles and focus and go to the role of emissions in Arctic sea ice loss in the 21st century.
Yeah, we're going to shift gears quite a bit after Robbie's talk. So like Dave said, we're going to shift to the Arctic, and also the method here, I'm mostly going to be talking about climate model simulations rather than in situ or satellite data. But yeah, I just want to say that most of the results that I will be showing you today are from this recent publication in Science Advances that's listed at the bottom here. But at the end, I will also be sharing some preliminary result that kind of follows from this paper. So I'm going to start with the classic Arctic figure, showing you the time series of observed Arctic sea ice area at the sea ice minimum in September from 1979 to 2022 from NSIDC. And the blue line is showing you the linear trend over that whole observational record. In addition, I've also added a trend line from 1996 to 2007 in pink, and from 2008 to 2022 in cyan. And you can see that over the period shown by the pink line, the trend in sea ice decline was larger than the overall trend, and that since 2008, the trend has been smaller than the overall trend, which is indicative of reduced rate of observed Arctic sea ice decline in recent years. And so this acceleration, followed by the recent reduction in Arctic sea ice, has already been reported in the literature. And these papers have shown that internal variability can explain these periods of high and low sea ice decline. Okay, so as temperatures are predicted to continue to rise, so this first figure here on the left is showing you just global temperature anomaly projections from CMIP6 models up until 2100. So we see, again, just general warming. Arctic sea ice decline is going to continue until it reaches ice-free condition. Again, the timing varies a lot across these models, but overall, we see a continued decline. And so for this study, I want to focus on the CSM model, Community Earth System model, which is developed at NCAR. And this plot is showing you the evolution of September sea ice area in the CSM1 large ensemble, which has 40 ensemble members. And the range of internal variability from these 40 ensemble members is indicated by the shading here, and the ensemble mean, or the forced signal, is indicated by the line. Now I've added the CSM2 large ensemble, which is the most recent version of the CSM model, and the one that was submitted to CMIP6. This one has 50 ensemble members. And the first thing that you can see is that they simulate very different evolution for Arctic sea ice from 1950 all the way to 2100. So that was quite puzzling when we first saw the results from those new simulations with CSM2. So just to recap, the CSM1 large ensemble uses the CSM1 version of the model and CMIP5 forcing, whereas the CSM2 large ensemble uses the CSM2 version of the model and CMIP6 forcing. So there are two things that are different between these large ensembles here. Now we also have these newly available simulations called CSM2 CMIP5. So like the name implies, those simulations are run with the CSM2 version of the model, but with CMIP5 forcing. So with these three simulations that we have, these three sets of simulations that we have, we are able to identify what part of the differences between those two large ensemble is due to changes in model version from CSM1 to CSM2, and what part is due to changes in forcing from CMIP5 to CMIP6. And what you can see in this figure is that at the start of the time series, kind of like before the start of the decline in Arctic sea ice, the two CSM2 simulations, so the black and the purple line here, are almost like right on top of each other. So we can say that the difference in mean state that we see prior to the start of the decline in the 1980s between the CSM1 large ensemble and the CSM2 large ensemble is really due to changes in the model version and the model physics that were changed between those two iterations. However, you start to see that at the turn of the 21st century, the two CSM2 simulations start to diverge. And just to make this a little bit easier on your eye, I've plotted here the sea ice area anomaly. So I've just removed that 1940 to 1969 climatology so that we can really focus on the rate of sea ice decline. And what you can see is that the two simulations that use CMIP5 forcing, so this purple and orange line, really have a similar rate of sea ice decline, again, around the turn of the 21st century. But the CSM2 large ensemble simulates a really accelerated loss of sea ice, followed by recovery around the years 2022. So we can really say that this difference in the rate of sea ice loss is due to forcing and not to model differences. I will skip this slide for now. So we found that one important difference between CMIP5 and CMIP6 has to do with biomass burning emissions, which I abbreviate to BB emissions in the text. So biomass burning emissions are emissions of gases and particulate from the burning of live or dead vegetation that can affect the climate through aerosol cloud interaction, as is shown in this little cartoon here in the bottom left. And emissions, estimates of biomass burning emissions that are used as prescribed forcing in climate models, they come from a variety of sources. However, starting in 1997, these estimates are based on the Global Fire Emissions Database, or GFED, which combines newly available satellite information on fire activity and vegetation productivity to provide a more realistic picture of biomass burning emissions. In CMIP-6, the biomass burning emissions were updated to include interannual variability instead of only using decadal means, which is what was done in CMIP-5. And so as you can see in this figure on the left, which is showing you the prescribed biomass burning emissions in the Northern Hemisphere, mid-latitude, and globally on the right, you can see in CMIP-5 that we were having these decadal values and kind of like a linear interpolation between those decadal values, but in CMIP-6 we have variations from year to year, but what we see is this very large increase in the variability when the GFED period starts. So we wanted to investigate what is the impact of this increase in interannual variability over the GFED period. So we conducted sensitivity experiments which we refer to as CSM2BB, where we averaged the biomass burning emissions over the GFED period from 40 to 70 north, and we used a fixed annual cycle to remove that internal variability while conserving the total integrated amount of biomass burning emissions. So this is represented by the green line here on the left figure, and the emissions pre and post GFED are exactly the same as in CMIP-6. So as a result, our sensitivity experiments have biomass burning emissions that are more similar to CMIP-5 over the GFED period. And we do this only from 40 to 70 north because we really want to isolate the impact of Northern Hemisphere mid-latitude wildfires on Arctic sea ice. And in the figure on the right, you can see that the global emissions are almost unchanged in our sensitivity experiment. And that is because Northern Hemisphere emissions make up only about 14% of global emissions. However, note that we found similar results by removing the variability globally instead of only between 40 and 70 north. So this really highlights the importance of those Northern Hemisphere mid-latitude wildfires on Arctic climate. So just to recap what we're working with here, we have the CSM1 large ensemble, the CSM2 with CMIP-5 forcing, the CSM2 large ensemble with CMIP-6 forcing, and then we have our sensitivity runs which use CSM2 and CMIP-6 forcing, except for biomass burning emissions from 1997 to 2014. And we have 10 ensemble members for these runs. Okay, so what is the response of Arctic temperature and sea ice to this change in biomass burning variability? So what we found is that the biomass burning variability in the Northern Hemisphere mid-latitude leads to variability in biomass burning aerosols in the Arctic. What this means is that these emissions that are happening in the Northern Hemisphere mid-latitude, these aerosols get transported to the Arctic, and we do see that same variability, temporal variability in those aerosols in the Arctic. However, these aerosols, when they're emitted at the beginning, they're fresh aerosols and they're hydrophobic, so they need to go through certain chemical processes to age until they can become hydrophilic, and then they can interact with water to act as cloud condensation nuclei. And then we see an increase in cloud droplet number in our sensitivity experiment compared to the control. So this map is showing you the vertically integrated cloud droplet number. And again, this is the difference of the CSM2BB minus the large ensemble, or the experiment minus the control. And you can really see higher amounts of cloud droplet number, especially over land in the Northern Hemisphere where those wildfires are occurring, but also those cloud droplet number get transported over the ocean as well. So larger cloud droplet number means increased cloud optical depth, means decreased shortwave radiation reaching the surface. So again, this figure is just showing you the net surface shortwave flux, and we see a reduction in the amount of shortwave reaching the surface in the northern hemisphere mid-latitudes. As a result, we see surface cooling in the Arctic. So this time series is just showing you Arctic temperature anomaly in the CSM2 large ensemble and our sensitivity runs. And you can see that over the GFED period, the Arctic warming is a lot reduced in the CSM2BB compared to the CSM2 large ensemble. You can also see this on the maps at the bottom that are showing you the trend in surface air temperature, and you can see that this very large warming in the CSM2 large ensemble is much more muted in the CSM2BB. And then finally, if we have surface cooling, we also see less sea ice melt. So this is just showing you again the sea ice area anomaly. And so we see less sea ice loss over the GFED period. And again, you can see these in these maps that are showing you the trend in September sea ice concentration over GFED. And these very large negative values are not present in the CSM2BB. So now you might be wondering, Patricia, how does removing the variability, so removing years where you have more and years where you have less biomass burning emission, can lead to an overall increase in cloud droplet number, surface cooling, and less sea ice melt? And that's because of nonlinear processes in aerosol cloud interactions that I skipped over quickly in this slide, but that I will talk about in the next slide. So I'm bringing back this figure that is showing you the biomass burning emissions in CMIP6 and in the CSM2BB, or sensitivity experiment. And I've kind of zoomed into the GFED period so that you can really see that difference between those high and low years. And the next few plots that I'm going to show are going to be time on the x-axis as a function of pressure on the y-axis, so vertical averages. And these are going to be showing you the differences, again, CSM2BB minus large ensemble or experiment minus control. And just to make this a little bit easier on your eye, because I've stared at these plots for a really long time and you can get lost very easily, I've added these lines here that are showing you the years. So the red line are showing you the years where there's more emission in the experiment than the control. And the blue lines are showing you years where there are less emission in the experiment than the control. And so this first figure on the bottom left is showing you the number concentration of aerosol in the primary carbon mode. So these are these fresh aerosols that are hydrophobic, that are freshly emitted from wildfires. And what you can see is that this pattern of like the red, blue, red, blue, red, blue line that we see in the emissions is also seen in the aerosols that are in the Arctic. Oh, I should have mentioned, these vertical plots are showing you Arctic averages in the summertime. And so we see in the Arctic this variability in these fresh aerosols, this red, blue, red, blue, red, blue pattern. However, when we look at the number concentration of aerosols in the accumulation mode, so these are these aged aerosols that have become hydrophilic and can interact with water to make cloud droplets, suddenly you see that this red, blue, red, blue, red, blue pattern is gone. So we mostly have the red years that are still there, but suddenly the blue years are gone. Why is that? And so we believe that this asymmetric response is a reflection of the observed nonlinear and saturated response of CCN to aerosol loading, meaning that in the red years, you start with a very low number of emissions and then you add a little bit more, and that makes more of a difference than if you start with that middle number and then you add even more. So at one point you start to saturate your system, and adding more aerosol doesn't necessarily translate in more cloud droplet number, if that makes any sense. So this is what this next figure is showing. Again, you see these red years are really highlighted in the cloud droplet number averaged over the Arctic. And again, the blue years are not so much appearing here. We also see that this results in larger amount of cloud liquid, not so much in cloud ice amount, and that is partly because these are summer averages, so more liquid clouds or mixed phase clouds that are happening in the summer. We also see an increase in cloud optical depth, and finally this results in that reduced air temperature that I've mentioned before. Okay, so I want to come back to the observations, which I've talked about earlier, and kind of ask the question of what do our results mean for understanding the evolution of observed Arctic sea ice? Because everything that I've shown you so far is in climate model world. And so I mentioned earlier that several studies have documented the steepening of the trend in Arctic sea ice since the mid-1990s, and then a smaller trend since 2007. And interestingly, this qualitatively matches the behavior of all 50 members of the CSM2 large ensemble. So this plot is showing you the sea ice area trend. So these are 20-year linear trend with the last year of the 20-year period shown on the x-axis. And you can see in the observations that the trend is increasing. It's getting more and more negative up until about 2012. And then the trend suddenly is reducing or getting less negative since then. And so it kind of makes this little V shape. And you can see that in all 50 ensemble members of the CSM2 large ensemble that are shown here, we also see this V shape. And so that is quite interesting, I think. And in contrast, these are the 10 members of the CSM2BB, so our sensitivity runs where we remove the biomass burning variability. And maybe there are a few ensemble members that kind of have this V-shape, but overall, we don't see a clear, coherent response across the full ensemble, which we would expect if this was a forced response to the system. And so this raises the question of a potential role of biomass burning emission in the observed Arctic sea ice loss since the late 1990s. Could this variability have also affected the observed sea ice decline? However, this is very hard to quantify because when we take into account internal variability, and these plots on the bottom are showing you sea ice area anomaly, so just the evolution of sea ice and all those ensemble members, we cannot say that the observed sea ice decline since the late 1990s is different from either the CSM2 large ensemble or the CSM2BB. So this doesn't allow us to say, yes, the accelerated sea ice loss that we've seen in the mid-1990s was due to increased biomass burning variability. However, our results do indicate that biomass burning variability can strongly influence simulated multi-decadal Arctic sea ice trend. So this should really be investigated further. And I'm going to talk a little bit more about that now. Just to wrap up, I've shown you that the CSM2 large ensemble simulates an acceleration in sea ice decline that coincides with the start of the GFED period. And then we conducted sensitivity experiment in which we removed the internal variability in biomass burning emissions over the GFED period. And we found reduced Arctic warming and sea ice decline compared to the CSM2 large ensemble when we removed that variability. The reduced biomass burning variability leads to enhanced cooling due to summertime nonlinear aerosol cloud interaction. And it's really the increased cloud optical depth during years with low aerosol burden that enhances cooling more than years with high aerosol burden. So there's this nonlinearity kicking in here. Finally, there are some indications of a biomass burning force signal, but again, the significant role of internal variability does not allow us to conclude that it is caused by the biomass burning variability. So what's next? The first thing that we're working on right now is to look at other forcings that have changed from CMIP5 to CMIP6 and what is their impact on the climate, because I've mostly focused on biomass burning here, but clearly there are other things that have been updated from CMIP5 to CMIP6, and maybe those also have an impact on how we simulate the climate. So I've brought back this figure here showing you the 3 sets of simulations that we've used. And then I'm just adding in green our CSM2BB experiment. And if you focus on this top panel here, you can see that by removing the variability, we kind of explain about half of the difference between the CSM2 with CMIP5 forcing and the CSM2 with CMIP6 forcing. So what is that other half due to? What are other forcings that could explain differences in the rate of decline? Or is it just internal variability? That's another good question. So these CSM2 CMIP5 runs are really essential to be able to answer these questions. And if you're with those, we're able to quantify how much of the uncertainty is due, again, to model difference versus forcing difference. And if you focus on this panel on the right here, you can see that the uncertainty due to the model in black is pretty small up until about 2020, 2030, when it starts increasing into the future. Whereas the uncertainty due to the forcing, which is in the light blue color, you can see this very large dip again at the turn of the century. So it's the forcing uncertainty is the forcing changes is adding a lot of uncertainty between those two simulations. And the biomass burning forcing, so the part of it that is just biomass burning in this dark blue, again, is explaining about half of that difference. But again, there are other things that are at play here that we would like to identify. And a way to identify this is we have these newly single forcing runs from the CSM2. So these are runs where, for example, these anthropogenic aerosol runs, only anthropogenic aerosols are evolving and all other forcings are fixed at pre-industrial level. And we do this with greenhouse gases, with biomass burning, and with everything else. And so these runs really allow us to kind of quantify the effect of a single family of forcing on the climate. So these are newly available runs that we're looking into to answer this question. Second, so the sensitivity of the CSM2 to changes in biomass burning variability really raises the question as to whether the lack of interannual variability in aerosol forcing in the pre-industrial control run and in the future simulation could be problematic. So at the moment, we have very little variability in aerosols in the pre-industrial and future, partly because we don't really know what happened prior to 1850, and also because we don't know what's going to happen in the future. But maybe lacking that variability could have impact on our simulation of the climate. And then finally, how does the variability and change in fire emissions affect the evolution of Arctic sea ice, including the mean state, trends, and variability? And so to answer these questions, we have climate simulations with an interactive fire model, where instead of just having prescribed biomass burning emission, the climate can respond and produce its own wildfires and wildfire emissions. So these simulations are on the way, and we hope that they will allow us to answer these questions. And so, well, that I will stop, and I'm happy to take any questions.
Awesome. Thanks so much, Patricia.
Yeah, thanks, Patricia. That was great. We'll open it up to questions.
I guess to me, there was maybe I think maybe an obvious question of like, has there been an increase in the variability in the biomass burning in that 2000s period that could explain that's going into that forcing data set? Or yeah, like that could explain the impacts that you're seeing there.
In the observations, you mean?
Yeah.
Yeah, I think, yeah, it's difficult to know because I think our observations of biomass burning emissions prior to when we had that satellite in 1997 are kind of based on proxies and a lot of approximations. We don't actually know. There is indication in the literature that in recent years or in recent decades, there's been an uptick in that variability, right? You can think of the recent years, you know, the Siberian fires or the Australia fires. So I don't think it's impossible that there has been a trend towards increased variability from the past to more recent years. However, I don't think it's as stark as it is in the way it's prescribed in the models, but clearly that might still be the case, and that might be part of the puzzle to try to explain why we have seen this strong acceleration in sea ice decline in the mid-1990s for sure.
Mm-hmm. Yeah, it's interesting. Thanks. And well, and just quickly, and I guess the opposite would maybe have to be true, right? If like a reduction in variability, which is maybe the harder one to explain.
That's an interesting one. So yeah, that's something that we've looked into because we again, you go from low variability to high variability to no variability at all. And so we actually ran some simulations where we superimposed variability over the future so that you don't get this drop in variability. And in terms of the sea ice, I can't speak to, you know, all aspects of the climate system, but in terms of sea ice, it made very little difference. which was I thought was interesting. So it kind of seems like the first few years of again going from these low kind of middle variability to highs and low, those first few years are kind of just enough to kind of shift the system in a way that then feedback mechanisms start to kick in, and then you have like that continuous sea ice decline. But yeah, it seemed like reducing the variability didn't make that much of an impact. However, that might depend on the mean state that you start with, a lot of other conditions. We just didn't find it in the specific sensitivity runs that we did.
Cool, thanks.
Interesting. Anyone else? No, nothing's coming up. Well, I would encourage everyone to go check out Patricia's paper. It's available online through Science Advances, and I'm sure there's some more information there if you'd like to follow up, or perhaps if you have remaining questions, you can contact Patricia afterwards. So yeah, we'll wrap it up there. Thanks everyone for joining. Again, this will be posted to YouTube probably tomorrow if you'd like to come back and rewatch any of these talks. The next Sea Ice talk is February 22nd. We have Sean Chua and Anton Steketee. They're from Australia, and they've developed a new ice tracking software in collaboration with Petra Heil. So they'll be giving a talk. And then we have Andy Mahoney from Fairbanks, who'll be giving a talk on some community-based research they've been doing on coastal landfast ice and community safety in that area. So thanks everyone for joining. And yeah, hopefully we'll see everyone again in a month. Take care.
Thanks, guys.
Just to say that next week's seminar is 3 early career researchers from Japan giving talks. So
yes. Thank you, Tavi.
Thanks, guys.
Yeah, thanks, Alex. See ya.
Yeah, see ya. I've got to run too.